Hello, everybody. Welcome to the second of the DARA E seminar series, where, as you probably gathered, we're kind of using a slightly new version of the Zoom tool this time. We're using the full webinar functionality, which means we're learning a little bit as we go along. So thank you for your patience, and apologies for starting a little bit late. We're also getting some issues with people who think they can join without registering. So if you share the message amongst people that they really have to register for these meetings so that they can join, otherwise they won't be able to, because that's part of, we're trying to obviously ensure that, you know, the right people join these meetings, etc. Okay, so thanks very much to Trish for organizing all of this and getting us up to speed on the new webinar environment. If people can't hear me or have any issues, then you know, put a message in the chat window. Also, there's a new feature on, if you joined us for the first one, there's a new feature this time with the webinar series where there's as well as a chat box, there is also a Q&A box, so a question and answer box. So this time, please, if you have any questions, if you think of them during the talk, then just pop them, type them into the Q&A box, and that will allow me to see them as chair, and I will therefore be able to call on you at the end of the talk in order to ask those questions. So hopefully that's the way it will work. So it's a pleasure to introduce Dr. Willice Obonyo, who, as the title suggests, was the first of the DARA sort of UK advanced students to complete and graduate from his PhD that he completed at the University of Leeds recently, graduating in January or December. And so it's a real pleasure to have Willice give the first of these talks from the DARA advanced students perspective. So I think without any further ado, I will try and hand over the host functionality to Willice. So Willice, I'm just going to make you the host, which means you can then start to share your screen and give the presentation. So the presentation should last for about 40 minutes, and then we've got, you know, a good 20 minutes or so for questions after that. Okay, I'll hand over to Willice.
Is everybody able to see my my screen?
Looks good to me, Willice.
Thank you very much. Thank you very much, everybody, and welcome to the second e-seminar organized by the DARA project. And today I'm going to talk about my project, the PhD project that I did while at Leeds, and a bit of my next step. So my project was on non-thermal radio emission from massive protostellar jets. Just a little bit of description of what my topic is that I was looking for synchrotron emission. So this non-thermal basically means synchrotron emission in the radio spectrum in the radio part of the electromagnetic spectrum. And I was looking for them from jets of massive protostars. Now, these are protostars that will eventually become massive stars when they are fully formed. And a massive star, just by definition, it should be a star that is 8 times the mass of the sun or more. And they have very special features, and that is why we are interested in them. Some of the features are that they die violently as supernovae, where they form either black holes or neutron stars, and also they ionize gas around them when they are forming, and that is to form forming H2 regions. So they have very special features, as we will see. This work was sponsored by DARA, as we are all aware, and was supervised by Stuart Lumsden, Melvin Ho, Julian Pittard, and also done in collaboration with Simon Passer, Stan Katz, and Catherine Johnson. Now, a little bit of my academic journey, just to share with you the past and then the future plans that I have. So I did a Bachelor of Education Science in Moi University, Kenya. and taught for 5 years. And within that period, I did a master's in physics on part-time basis, also at the same university, Moy University. Later in 2013, I went to University of Cape Town and did a master's in astrophysics and space science. After that MSc program, I joined the DARA family as a basic trainee in Kenya. And that is how I transitioned from optical astronomy in South Africa to radio astronomy, where I studied massive star formation. And after my PhD, I then went to University of Manchester as an intern. At the University of Manchester, I described as a research associate in scientific computing, and some of the work that I do involve building up containers, computer containers, testing products of observations like Meerkat, testing pipelines and new softwares that are meant for radio astronomy. In October this year, I will be in Pretoria as a postdoc, Sarao postdoc, working with Professor Roger Deans. You're welcome. Now, my research at Leeds, like I've said, is on star formation, and just a little bit of what star formation entails. So stars form as a result of collapse of a large cloud, as shown here. So what you see here is a simulation from the University of Exeter astrophysics group, and they have a cloud here that collapses under the influence of gravity. As the cloud collapses, what you see here are filamentary structure. You also see dense clumps shown here in yellow. You also see junctions of filaments, and these dense clumps are where stars form. Now, there's a little bit of challenge in massive star formation, and one of the challenges, as you can see here, as the cloud collapses, there is fragmentation that takes place. So one of the challenges in massive star formation is called fragmentation problem. And it's a problem because if you look at the typical temperatures of this gas and the number densities, then you realize that the clumps should have masses that are below 5 solar masses. So then the question is, how do massive stars form from such smaller clumps? A number of theories have been put in place to try and explain this. And one of the theories is that it's called monolithic collapse, where just one of these clumps collapses and continues to accrete mass. And the continued accretion of mass is believed to be through an accretion disk, which is tightly connected to jets. Another theory that is also in place is that instead of just considering one of the clumps, then you consider a group of clumps that are held together by gravity, which you could call a protocluster. And then this group then accrete mass from a larger, because they have a larger gravitational field, so then they can accrete mass from the larger field. And then once the material is within the reach of the individual clumps, then they can compete for the gas. And that is why this method is called competitive accretion. There is also another method where massive stars are formed, smaller stars are formed, and they're in a cluster, and that cluster has higher stellar densities. So if the stellar densities are high enough, then these stars are closer together, and as they orbit each other, they have the potential of losing angular momentum and merging into one big star. So these theories have been put up to try and explain how massive stars form. But as we will say, I'll just concentrate on one of them. Of course, possibly both competitive accretion and monolithic collapse that I talked about are both into play in the same system, for example, in the protocluster. Now, this one is just to show how star formation sites look like. What I'm showing here on the left is the simulation, a snapshot of the simulation. So you see here the filamentary structure, you see the junctions of filaments, and you see the clumps here, and possibly a protocluster, maybe. And also you see on the right is a real observation, a snapshot of G305, a star forming complex. And this gray map here shows 5.8 micron, which is dust tracer. So you see dust distribution around here. You see the filamentary structure here, similar to what we say here. You see the clumps here, and you see also formed stars. And apart from that, you do see here that we have the 5.5 gigahertz emission traces, the contours here, traces free emission. And you see that these free emission are coincident with the clumps. That is to say that is possibly where the stars are being formed. And also something that is interesting about this picture here is you see that around the newly formed stars, there's an evacuation of material. So it's like most of the materials are driven away by radiation pressure. So the pressure around these objects are also very high, which we'll see in the next slide as one of the problems of massive star formation, apart from the fragmentation problem. So now just a summary of evolution of a protostellar core. So a protostellar core would start from what is called a prestellar core. So others describe it as starless core, and then it collapses under the influence of gravity. After collapsing, then there is compressional heating. So the heat generated as a result of compression. And then after that, then a newborn star is formed. This is a standard way of looking at it. And but then in massive stars, there are a bit of challenges. One of them I've mentioned is fragmentation, but there's another one, which is also another big problem. It's called radiation pressure problem. So these massive stars, as they form, it reaches a point that they are hot enough to emit UV radiation that has the capacity to drive away or stop any further accretion. There's a limit that is theoretically set to around 40 solar masses. But then we see in observation that there are stars that are greater than 40 solar masses. If you see this plot here on the left, this is a simulation by Krumholz et al. 2009. And what they show here is the resultant force. So there is the gravitational force or pull as a result of these clamps here. And there's also outward radiation pressure force as a result of pressure from this central object. What you do realize is that the arrows show the direction of flow of materials, that around where the pressure is greatest, there is very little flow of materials towards the central object. So there is no accretion or little accretion taking place. Major accretion takes place to where regions where there's little pressure. So if we have a disk, for example, then there is likelihood that there's going to be more accretion around towards the disk, following the disk, instead of along the directions where pressure is greatest. So this is one big problem in massive star formation. Now, one of the theories that have been suggested to explain how this can be overcome is high accretion rates. So there's a theory trying to say that if the accretion rates are high, then there is a potential of the incoming material to have higher pressure, the mechanical pressure, to overcome the radiation pressure and still land onto the central object, and then we can get the massive stars. So that has sort the problem out a little bit, but then as you will see from observation, we do realize that we don't achieve such accretion rates that are as high as 10 to the power minus 3. Now, about the same time, Hosokawa and Omukai also did a simulation, and their simulation gave a very interesting result. If you look at this plot here, what we are showing here is it's the radius of a protostar. I will call it a core, so the radius of the core, and then you have mass here. So the mass, the core is radiative to mean that it's not possible to have convective currents which are responsible for generation of magnetic field. But then there is a phase within the core as it evolves and increases in size, where there is very greater increase, exponential increase, until the outer part behaves like it's a convective envelope. So it behaves like a red supergiant cool on the outer part with convective envelope that has the potential to generate magnetic field. And then later it contracts and then increases again as accretion continues. So the reason why this is interesting is two. There are two reasons why this is interesting. One, once there's the expansion or the swelling of the envelope, then the interior part of the core can still continue to accrete even though there is pressure. So then the outer part then allows for accretion from the outer region. And then once it's within the envelope, then it can be accreted to the core or the protostar. Another reason that is interesting is that at the only point where these protostars, massive protostars, can have magnetic field, and that is, as we will see, depending on the model of the jet, is at this phase where it has a convective envelope, where the central object has magnetic field in it. So it has a very significant result in massive star formation. Now this here is just an illustration by Carrasco-Gonzalez showing how jets are formed, disk jet systems in stars. So if you zoomed into one of those clamps and then there is a protostar forming, and what you should say is that you should see a central object. If we're able to do that, you should see a disk around it, and you should see a jet of materials ejected from the central object. Now, these jets are very significant. One, as you can see here, the region around the central object is very dusty. And because it is dusty, it is very difficult to observe the central object and the disk. And so the easiest object to observe is the jet because of the large scale due to resolution. Another important function of these jets, if you study them, is you say that these points here, we can call them knots or lobes, they are ejected at different intervals. And one of the theories is that they point to the accretion history. So that accretion that is taking place here does not just go in smoothly and uniformly, but then it goes about in bits. And that is believed to be because that the accretion of materials are also falling in as clumps, which is very significant because we can't, in observation as we have it now, we can't see the mass loss rates that we expect from theories. But then because of the clumps that are coming in large bits, then it's possible to attain the accretion rates that are theorized by Krumholtz and the Hosokawa and the Mukai team. Another very important, significant function of these jets, as illustrated here, is that they take away part of the angular momentum. Now, if a large cloud collapses and forms this central object, there should be, as a conservation of angular momentum, the central object should rotate so fast that finally this central object should break apart. But that doesn't happen. One, because of the accretion disk that take away part of the angular momentum away from the central object, and also these jets which have been seen to be rotating these days. And recent observation shows that they also rotate. Now, apart from that, we do see, if you look at this simulation, this artist impression, what you see is that there are lines here representing magnetic field. Those magnetic fields are very significant because they explain how these jets are driven. So jets are driven in two ways. One of them is called magnetically driven jet. Another one is called radiatively driven jet. Radiatively driven jet depend on radiation pressure from the central object and interaction with ambient medium. But I won't say much about it because that's not my area of focus. Now, my area of focus was on magnetically driven jets. And this magnetically driven jet can be driven in two ways. There are two models that try to explain them. One of them is called disk wind. So in disk winds, we have magnetic field that is threading the disk. And then as material fall in, they interact with the magnetic field, and then they're ejected away, collimated by the magnetic field and accelerated by the magnetic field. In another theory, there is what is called X-wind. In the X-wind, both the disk and the central object require magnetic field, and ejection of material takes place at a region that's called X region in between the inner part of the disk and the central object. So at that point, there is a potential region in terms of magnetic field, and then materials are ejected and blown away. And that is why I was interested in identifying evidence of magnetic field using synchrotron emission. So synchrotron emission is this emission that we get when there is an interaction between magnetic field and charged relativistic particles, as I will illustrate. This is just an illustration of a magnetically driven jet. So what we see here is a disk, it's an X-wind. You have a central object, which is the star. It has its own magnetic field, and you have a disk here. And then there's magnetic field through the disk, and there's magnetic field of the central object. The two fields interact, and we have an equipotential region around which the particles of the jet are ejected. Now, any material that is on the inner part of the disk of the X region is accreted towards the central object, and any material out of the X region is ejected and forms the jet. Now, this is interesting, and it could be tested probably in the future if resolutions are high, because then in this theory here, in the disk wind model, then we have accretion funnels. So most of the materials are accreted and they hit this central object. I think in low mass stars, we see X-rays as a result of this hot UV spot here. But I think because of observation limits, we still don't see this in massive stars. Now, on the right here, we show disk wind that was proposed by Blanford and Payne in 1982 and customized for massive star formation by Pudris and Norman in 1983. What we see here are magnetic field lines. You see an accretion disk. As the materials flow through the disk, they interact with the magnetic field and they are ejected and flows to form disk winds. Now, in 2010, Carrasco-Gonzalez made a very significant discovery, and they observed this source called HH881 for a very long time. And because they observed it for a very long time, they then achieved a significant signal-to-noise ratio. And when you receive such a signal-to-noise ratio or data of such signal-to-noise ratio, then it's possible to identify the nature of the emission. And what they found out is that this source here emit emission that is synchrotron, polarized synchrotron emission. That is a sure evidence that there is magnetic field, and they show here that the polarization is in that direction, and then the magnetic field is along the direction of the jet. So now this was the first jet to be imaged directly to show that there is a magnetic field along the jet. Now what I'm showing here on the right is illustration of the kind of emission that we get from these jets. So on here we see a magnetic field, and we see a charged relativistic particle spiraling it and emitting radio waves. And these waves here are synchrotron emission, and that is why I'm illustrating them here. But in the core, we see free emission that is emitted when a particle, charged particles interact with another charged particles and accelerated by it to emit free emission. Now my work largely was to identify this emission, synchrotron emission. But then not every group is lucky to have such kind of observation, deep observations. So because we were studying a large sample of 15 objects, we couldn't get the time to observe one for such a very long time. And so we opted to use another different technique that is called spectral indexing. So besides the technique that was used by Carrasco-Gonzalez, which is polarization, there is also spectral indexing. Spectral indexing requires that you observe that source at more than one frequency band. So as an example, in this case, this source here was observed at 3 different frequency bands. So that is somewhere around 350 megahertz, around 500 megahertz, and around 1,500 megahertz. So what you do with the 3 frequency bands is that you plot a graph of frequency, flux versus frequency in log scale, and then the slope of this gradient, the slope of this plot here will tell you whether the emission is synchrotron or free emission. If the gradient is negative, then the emission is synchrotron. If the gradient is positive, then the emission is free emission. And now here, instead of using the plot, because the plot only is for a few points, so you can get that data point, and that data point, then you can, if you can get the image at the different frequency bands and then get the ratio, you still use the same formula, but that get log of the differences. And then if you do that, then you get what is called a spectral index map. This spectral index map is basically this, but for every pixel. So for every pixel, you say what the spectral index is or what the gradient is. And what you do see here is that the core is thermal, and whatever is minus 0.1 and above is classified as thermal. And when the spectral index or the gradient is lower than -1, then minus 0.1, sorry, then we classify it as synchrotron emission. And when you compare this plot here and this plot here, what you do see is that we have a thermal core where there is no magnetic field in this case, but then you also have a thermal core here, which does not show evidence of magnetic field. So these 2 techniques give the same result, but this one has the capacity to study a number of objects, as opposed to this one, which will require long observing time when these telescopes are also in high demand. Telescope time is also in high demand. So we used this technique here to show to identify whether our emission is thermal or non-thermal. Now, my work was done as a continuation of previous studies. And this study was done by Simon Purser. So Simon identified 60 massive young stellar objects. And they observed them at C-band, which is 6 gigahertz. And they also observed them at Q-band, which is 44 gigahertz. C-band data was observed in 2012, while Q-band data was observed in 2014, and bits of them in 2015. Now, what they did find out from their study is that of the 60 objects, some of them showed evidence of non-thermal emission, synchrotron emission. But then there was also only a small group of them that they identified to have synchrotron emission. A large portion of the sample had free emission. But as you can see from my previous slide here, synchrotron emission, which has the negative spectral index, is brighter at lower frequencies. As you go to lower frequencies, it gets brighter and brighter. And that is why we decided to identify 15 MYSOs, 15 out of the sample, to observe at 1.5 gigahertz, which is L-band, so that we could identify more of this synchrotron emission if they are there. And the criteria that we used to identify the 15 MYSOs are that we we identified the brightest at 6 gigahertz so that we could also detect it at L band, which is a lower frequency. We limited ourselves to 7 kiloparsecs for resolution purposes, and also identified sources that are greater than 2,500 bolometric luminosities, so that we only identified massive protostars. Now, these 15 objects were observed using the JVLA telescope on a configuration. That configuration we have at L band, we have a resolution of 1.2 arcseconds. Now, what we did find in some of the sources is that some sources had non-thermal emission. This is one of the sources that we studied called AFGL 4029. This source here, if you look at it, the central part has a thermal emission or free emission. And you say that we have the L band emission, C band emission, and Q band emission. The spectral index is 0.28. And there was a previous observation, which is a little bit brighter, but we'll talk about this later because it has some interesting effect on the result. But also what we found out is that on the left, source B here had non-thermal emission, a spectral index that is lower than -0.46. Also on the right, we had another source, source C, which has a spectral index that is lower than -0.38. So this source G138 has a jet in the direction, and the reason we are convinced that these are not artifacts is because it has an optical jet. Also in the infrared, it shows in that direction. That's why we are convinced that this is a lobe, and this is a lobe, and C, and the central object is the core of the jet. Another source that we studied is G0944637. This source here was a little bit interesting. We saw two thermal sources, source A and source C, and also non-thermal lobe. So we saw a non-thermal lobe at E, another non-thermal lobe at D. So we believe that there's a jet in this direction and another jet in this direction. So it has multiple jets, and that told us that some of these sources could be having multiple jets, probably a binary system. But that is for another further study to find out. But if we did also look at previous studies by Navarrete et al. 2015, who studied this object at infrared and using 2.12 micron emission. This 2.12 micron emission is a molecular hydrogen emission that traces shocks. So we have here a shock tracer in that direction and another shock tracer in that direction, telling us that there's a jet in that direction and another jet in that direction, giving us more confidence in the study. Now, what we found ideally is that 40% of the sources have non-thermal lobes. And these non-thermal lobes, we estimated their magnetic field and found out that the magnetic field is roughly 0.5 plus or minus 0.2 milligauss, which is comparable to the result that Carrasco-Gonzalez team found in 2012 using polarization, 2010 using polarization. So we are a little bit convinced that this is quite okay. We also found that they have energies that lie in the range 10 to the power 41 and 10 to the power 42 args. But what we did found out also is that all the cores are thermal. And I'm just showing here one of the cores for G1267144. And here we see a core that is thermal. We see infrared nebula in that direction, but we don't see the lobes. We don't know why we don't see the lobes, whether it's an issue of sensitivity or it doesn't just have lobes, or it doesn't just have magnetic field or lobes. It's difficult to tell non-thermal lobes, that is. But we see that it has a spectral index of 0.82 plus or minus 0.02. Also, we also found out that in previous study at 6 gigahertz, it has a morphology that is in that direction, which is sure also evidence that it has a jet in that direction. Now, another property of the cores that we estimated is that we found the mass loss rates so that we could compare with the theories, and we found that mass loss rates lie in the range of 10 to the power minus 7 and 10 to the power minus 6 solar masses per year, as you can see here. And this, if you compare with the accretion rates, because there is a ratio of the ejected materials, part of the material that is accreted is ejected, and different researchers have different ratios. But then there was a previous study in 1995 by Hartigan, which estimated the ratio to be around 1%. Using this 1%, we found out that the accretion rate is roughly 10 to the power minus 5 and 10 to the power minus 4, which is still lower than 10 to the power minus 3, which is what is recommended for accretion of massive stars so that they can form. Now, another property of the cores that we established is that the jets have ionization mechanism that is similar, and all the jets are collisionally ionized. Well, this plot here shows radioluminosity versus bolometric luminosity, and the radioluminosity scales all the way from low mass stars to high mass protostars. And what that tells us is that the low mass jets and the high mass jets has a common ionization mechanism. The line we are showing here is the line of photoionization. So if there was photoionization in high mass objects, because they are bright, they are very hot, then it should be around here or more. But because in low mass stars also the photoionization is lower, has no potential to give the radioluminosity that we find. And because of that, then we do get, because of the common ionization mechanism, which is collisional, then we do believe that these jets here have similar properties as low mass stars. And because of that, then they should also be having accretion disk, just like low mass stars. Whenever you see a disk, there is a jet associated with it. Also, in a recent study by Fedriani et al., they found out that only 5 to 12% of these jets are ionized, which also convinces that it's largely collisional ionization. Now, this study is okay, but it has a bit of uncertainties. And the main source of uncertainties is variability. So I showed this plot here in the previous slides, in one of the previous slides. And what you do find here is in a previous observation, it appears as if this source was bright at this frequency. And why couldn't that be? Why could that be? Possibly it's variable, so it changes the brightness with time. And because it changes the brightness with time, it's difficult to establish the spectral index and of course the nature of the emission very accurately. And that is because if we only had this point and didn't observe the source at L and C band, then and only had it at Q band, then we could be convinced that the gradient is that, and so the emission is possibly a H2 region or non-thermal, which is misleading. And so because of that, we did another observation. Also on the right here, I showed this lobe E, the lobe of the jet around this along this direction. But this lobe, if you look at it keenly, you do find that there's a little bit of displacement. If we observed this lobe, this source later, say 2020 now, probably the lobe is here. And it could give us a little bit of a wrong impression that the lobe is that there are two lobes and one of them is non-thermal and one of them is thermal, when actually the lobes are non-thermal and it's only displaced. So the main source of this, the main source of uncertainty of this study is variability, both positional variability and flux variability. And because of that, then we put in a proposal to observe the sources again, and so that we could establish how the prevalence of variability. We put in a proposal to observe 11, but only 4 were observed because of the little telescope time that we had. And what we did find out is that 2 of them showed considerable variability. S255 NIRS3 showed very significant flux variability. It was in outburst at the time. And what we did, the core here, what we show here on the right is its flux with time. It had been monitored by Cesaroni et al. 2018, but we also observed it in 2018, the early months of 2018, and we found that it's still in outburst, so it's still on the rise. What we did find, which was quite puzzling, is that as the flux rises, the spectral index goes down, which we interpreted as opacity goes down with time. So that is quite interesting, as we will still continue, because you'll find out that what is expected is that as the flux rises, the opacity should rise. But this was interpreted to mean that there is an ionized bubble of gas that is expanding with time. So as it expands, the opacity goes down and it brightens. That is how it was interpreted by Cesaroni et al. This source here has a core that is thermal, which is what we are showing here on the right, but it also has lobes, which are non-thermal. So which means it has magnetic field here and here. Now, another source here that we found out which showed significant positional variability is W3IRS5. And what we are showing on the left here is a model that we used to find what we call precession. So what we are saying is that this jet does not just churn out materials in a straight line, but it also moves in a conical manner. And when we did fit a precession model based on this, where the observer is that, and it's on the plane of the sky at 90 degrees to the line of sight of the observer, we found out that the jet is doing two things. One, it's the lobes are moving away from the core, but apart from moving away, they're not moving away in straight line, but they're moving away in a wiggly line, which is showing evidence of precession. So we found out that it's precessing at an angle of 10 plus or minus 2 and precession period of 40 years. And we also found out that the average velocities of these lobes is 460 plus or minus 60 kilometers per second. Just to show a little bit of details, whatever we are showing, the contours that are shown in gray were observations of 2018, and the contours that are shown in black are observations of 2012. So there was a 5-year gap between the observation of 2012 and the observation of 2018. What we also found out is that these lobes do not just move at the same velocity all through. What we found out is that the lobes that are very close to the core is around there. The lobes that are very close to the core are moving faster generally, but the ones that are as they are further away from the core, they're moving faster and faster and faster. And we interpreted this to mean that the lobes accelerate with time after ejection from the core. Further out, we find that the lobes are generally moving at a slower velocity. And this could either be as a result of interaction with the ambient medium. So as they move away, they interact with ambient medium and they're slowed down, or they just lose energy as they move away from the central object. So we found out that the lobes show acceleration, but they also decelerate as they move away from the core. Now, we did simulate the properties that we observed. And to simulate the properties and understand how they behave, we first started with a steady jet. And a steady jet here is a jet that is moving at constant velocity, churning out mass at the same velocity. So at the same rate, mass loss rate is constant. And we injected here a stream of charged ionized particles, and injected them into a stationary ambient medium. And what we found out is that if you calculate the fluxes of this source as it evolves, then the fluxes are relatively steady as well. Also, the spectral index is relatively steady, even though it can change a little bit, but they are relatively steady all through the evolution period of a steady jet. Now, if you change that, and instead of injecting material at the same velocity and same mass loss rate all through, but then mimic an outburst in which you first start with a jet of moving at the same velocity, but of a lower mass loss rate. So you're putting in just a small portion of charged particles, but later inject more particles that are charged to mimic an outburst. What you see is that the flux also rises as expected, even though there are a little bit of changes, but it rises. And it remains high even after the outburst. And I think this is because the introduced charged particles remain in charged state for a longer time. So the combination takes time slowly. I think it will go back to normal or to lower value once most of the charged particles are either recombined or flown off the grid. But then also, if you look at the spectral indices also behave in a similar manner. And that is why the result from S255 is interesting. When you simulate the outburst, we find out that the flux increases and spectral index also increases in a similar manner. So what we expected then in S255 as an outburst is that the spectral index, should also have a higher value as the outburst progresses. And now that is why we are thinking that this could be an interesting result to show that maybe there is a magnetic field at the core. We can't just detect it, but possibly there's a magnetic field at the cause of this massive protostars. So here is a simulation that was done by Doherty et al. In 2003. And what they did do is that they simulated both synchrotron emission and free emission at the same time. And so if there is magnetic field and relativistic charged particles around the core, then what we expect therefore is that as the outburst comes in and progresses and it becomes more intensified, then the synchrotron emission should intensify as well, of course, as free emission, and that has the capacity to lower the spectral index or the gradient of this with time, which makes us to believe that what we are seeing is an indirect indicator of magnetic field at the core of these jets. Now, in conclusion, therefore, what we found out is that massive protostellar jets have non-thermal lobes, and of course they emit non-thermal radio emission. Some of the jets exhibit the lobes, whose energies are whose magnetic fields are roughly 0.5 plus or minus 0.2 milligauss, and energies of 10 to the power 41 and 10 to the power 42 args. And they play significant role in massive protostellar jets. And also that MYSOs have high accretion rates. And when we mean high here, we don't mean the one of the theory, but it's higher than low mass case. Low mass case have mass loss rates that are roughly 10 to the power minus 10 to 10 to the power minus 7, thereabout. So of course, the high mass protostars have mass loss rates that are 2 orders of magnitude higher than in low mass protostars. And they also have jets that precess. Now, my future work will depend on the next step, but some of the work that can follow what we have done is 3D simulation of protostellar cores, high resolution follow-up of these observations with eMarlin, so that possibly we could tell exactly how small the jet is because of resolution reasons. Maybe what we are seeing is a large region around the core. And then L-band study of the observation using the southern plane, and that is using meerkat observations. Now, in the immediate, because I'm going to University of Pretoria as a postdoc, the first task will be to study a sample of MYSOs on the southern hemisphere. And there was a galactic plane survey by meerkat at L-band, so that data is already there. Also, there is this proposal to observe the southern hemisphere at around 12 gigahertz in this MEAGAL survey, according to this study here by Thompson et al., proposal by Thompson et al. 2016. So there is future for, there is a room for future development of this project in further details. And I just want to say thank you to DARA leadership for the opportunity that you've given us and you've given me, to be specific. And thank you to Melvin for not only being my supervisor, but also a guide and let me say a father figure to us here at Leeds, and Trish for being very motherly all through my PhD period. Thank you very much, everyone, for listening.
Okay, thank you very much, Willice. Very good tour of your PhD work at Leeds. Let me just, okay, as I work out what I'm doing. What do I want to do? Let's get me back as the host. Okay. So that was hopefully gave you a good insight into you know, the kind of ingredients and level of the work in a PhD. I would say Willice's was a classic sort of Leeds PhD, a combination of state-of-the-art observations from the big telescopes like the VLA around the world, but combined with a little bit of simulation work as well, so that you get a real range of skills during your PhD. Okay, so there's been a couple of questions come in already. So again, anyone who wants to ask anything, you know, whether it's specific to the details of the project or more general about, you know, DARA PhDs and that kind of thing, or astrophysics careers in general, then please type them in. We're happy to answer any of these. So we're gonna try and take a question. So again, we're learning how to do this. So we'll see what happens. So I've got a button to press here for each particular question that's been asked. So the first one came in from Solomon Apake in Ghana, who's one of the students currently waiting for the lockdown to end so that he can also join us at Leeds for his one-year Masters by Research. So I'm not sure if you're, when I press the button, you'll be able to ask the question yourself, Solomon, but let's see what happens. So Solomon, are you able to unmute yourself and ask the question now?
Melvin, I think you may have to click on Solomon and allow him to talk.
Okay, I'll find him. Yes, allow to talk. There you go, Solomon. I think you can unmute yourself now and ask your question.
Okay, can you hear me?
Yes.
Okay, so thanks, Dr. Willice, for your presentation. I really enjoyed it. So I have actually 3 questions. So the first one, do you have any idea of the magnetic field strength of the ambient medium around and in those observed jets that you studied? And if you do, what kind of interaction also goes on between those jet materials and then the medium around the protostar? I was thinking maybe it's ionization. So that's the first one. I don't know if I should go on with the second and then the other one.
I think let Willice answer that one first. Willice, did you catch the question?
Yes, I got it. Thank you very much. Yeah, so yeah, this is a question that is very also discovered a little bit. And the reason is these jets are known now, especially HH881 is known to have magnetic field and there's special magnetic field lines within the jet. But it's also possible that if you have a charged relativistic particles and it interacts with ambient medium, it can give the same results that we were seeing. So we also looked at the magnetic field of ambient medium in the star-forming region. There was work that was done by Fisher et al. In 2003, and they estimated the magnetic field in these regions to be roughly 0.1 to 10 milligauss. So I agree, it's difficult to tell whether the magnetic field is ambient or not, but we are convinced that they are within the jet, because if we look at the infrared emission, we see that the direction of flow is similar to that of the jet. And when we look at shocks like the ones I showed you from 2.12 micron molecular hydrogen emission, it's in the same direction. So we do believe very strongly that what we are seeing are within the jets, and not just as a result of interaction of charged particles and ambient magnetic field. But as I agree, it's very possible that if there's an ambient magnetic field and charged particles and they interact, we still can get the synchrotron emission of the magnetic field and the energies that we quoted. Yeah. And also the ionization also is possible because these particles move very fast at 500 kilometers per second. If they interact with ambient gas, they can ionize them collisionally still, just as we mentioned. But even this can happen within the jet or with ambient medium, there is interaction, yes. I hope that answers the question.
Yes, it does.
Okay, Solomon, do you want to add your follow-up question?
Yes. Okay, so I happened to read a paper, and you mentioned the sources and some of the samples displayed evidence of variability. I was asking, I mean, are those various variabilities due to the morphology of the regions you studied? Maybe the density that were different, or those various parameters that caused those variabilities. And the third one is on, okay, maybe you go on with that.
You're breaking up a bit there, Solomon. I think we'll let Willice answer the sort of second part of, I think, the origin of the variability, whether it's morphology or not. Willice, you can also unmute your video, I think, so people can see you talking. So turn on your video, I think.
Unable to start video.
you're unable to. Okay.
Yeah, so the variability that we're talking about here, we think is as a result of accretion. So the material that fall in, what we believe is that it doesn't fall in uniformly so that there's smooth infall of material. But we think that they fall in clumps, of course, because these star-forming regions are also clumpy. So it could be accreting mass in clumps, and this is manifested in the radio emission that we get. So we think it's a result of accretion. So if you say here morphology of the region, if that means the clumpy nature of the region, then that's okay. But we think that it's because of the clumps, and these clumps fall onto the accretion disk and then accreted as clumps, or the effect is then transferred to the central object and also on the jets.
Okay, maybe let me follow up one as well, because you had the source that was conical, the jet that was conical. You know, what do you think's going on there? Why is it processing around? I don't think you mentioned it.
Yeah, that could be as a result of maybe being binary, or maybe evidence of binarity. Or it could also be, I mean, there are other theories that are also used to explain this conical, the precession nature, maybe a warped disk. Yeah, so it could be as a result of a warped disk or as a result of binarity. Yeah.
Yeah. Okay. Good. Okay. I might try and experiment with the next one and making you the host, Willice, and then see if I can still control the Q&A. But because I'm not quite sure if that works or not, so that people can see you answering the question. So the next question is from Gloria, who's another one of our master's students who's waiting to join us to come to Bristol, I believe. So let me just do that one and try and allow Gloria to speak. Okay, Gloria, would you like to ask your question to Willice, and I'll hand over the control to Willice as well. Gloria, you'll need to unmute yourself first, and then you should be able to ask the question. Maybe I can unmute you. No? Gloria, do you want to ask your question? If not, I can ask for you. Okay, let me ask Gloria's question on her behalf. Maybe she can't hear me. So she would like to know what kind of software you use to simulate the radio emission from the protostellar jets. You know, which programming languages are you using for your work?
Yeah, so the programming language that was used to write the simulations of code is C++. And I didn't write it, it was written before, so I just used it. And which programming language did you use for your work? So most of the work that is presented here is done in Python programming language, but the simulation was purely in C++ and a bit of C.
Okay.
Yeah.
I'm just experimenting, Willice, and handing the host of the meeting over to you. So if you should be able to turn your video on now.
Yes, it's on now.
Okay, that's good. And I'll see if I can continue with the questions. Okay, so yeah, sorry, Gloria, I just saw your message. Sorry that you couldn't turn your audio on. Hopefully that answered your question for you. Okay, another question here from one of our students in Mauritius, Miro Sade. So he's currently doing the MPhil over in Mauritius, and originally from Mozambique. So Ramiro, let me try and allow you to talk. Oh, Willice, you'll have to allow Ramiro to talk now. So if if you click on the participant list and then the attendee list.
Participants, yes.
So, and then scroll down to Ramiro near the bottom. You should be able to click on his name and then say allow to talk. You can see that we're learning how to use these tools as we go along here. Yeah.
I can't do that. I don't know why. Is it the participants?
No,
Okay.
attendees. So if you click over to the attendees, then you see the list of attendees. You scroll down to Ramiro, click on his name. So he's near the bottom.
Okay, allowed to talk, okay.
That's the one. So if Ramiro, you unmute yourself, you should be able to speak. Yeah.
Yes. Hello, Wilson, and congratulations for your presentation. It was very interesting. So during your presentation, you mentioned that your lobes have some kind of acceleration. And I would like to know if during your observation, could you notice some kind of Doppler shift? And if so, could you use this Doppler shift to start the periodicity of your precession? I would like to understand it.
Yeah, so according to what I presented, it's not a single lobe that has been followed. It's different lobes, different locations. And because they have different velocities at different locations away from the core, we just infer that they should be accelerating. I know it's possible if you do emission line observation to do check the velocities and do that in details. But with the current observation, it's still not possible to do that kind of work. I think in the future, it will be possible to do line emission observations and then get accurate velocities, actually better ones, and identify all this idea that you're saying. Yeah. But that I think is for future.
Okay, thank you.
Okay. Solomon has a third question. So Solomon, do you want to ask that one? You can still unmute yourself, yeah.
Yeah, so again, in your paper, you said, so for the free emissions at the Q band, that you use the various parameters associated with them. So you use those various ones for the spectral indices. And then you said that the estimates were unknown. Those various parameters that you used, they were unknown, and hence could have reflected in large errors. However, you used it anyway. And then you said for the SEDs of those various scores related with the Q band, you didn't see any unexpected behaviors in those various SEDs. I don't quite understand that. Looking at the graph, I couldn't really understand what it really meant. So if you could explain that.
I don't know if you caught that, Willis. There's still a lot of interference on the line there, Solomon. You might need to type the question.
Type it.
Yeah, if you type the question again, Solomon, then we'll come back to it. Okay, we'll come back to it later. Okay. Okay, so Matthias had a question about the significance of the precession of the jets. I don't know if you just answered that already with your idea of the binaries. I don't know if you want to add any more to that, Willis. But
yeah, I think it tells us the nature of these objects, and it tells us that either they are binary, or it's also an indirect indicator of a disk and a warp disk in this case.
Yeah, I think those are the two interesting mechanisms. Okay. But yeah, thanks for that, Matthias. Sorry, I didn't go to you live, but I think I think we kind of addressed that one pretty much. Evan has a question, a more general question. Again, you'll have to give him permission. Sorry, Willis.
Okay.
Making you work now after you've done all the work.
Yes, Evans. Is it Evans?
Evans, yeah. Evans, do you want to go ahead?
Yes, hello, can you hear me?
Yep.
Okay, congratulations, Dr. Obonyo, for the successful completion of your program. And I just wanted to ask this question, is more generic. What sort of challenges did you encounter during your PhD journey, and how best did you handle them? Knowing that this sort of academic journey has a lot of sort of challenges associated with it. Yeah, thank you.
I think any research, and this being one of them, has a number of challenges. One of them is understanding the software. I really had a bit of difficulty understanding how to go into C++ code and understand what it's doing so that I could know what's going on. I think that was one of the most challenging times, because initially I would just take the whole code and go home and read it, but not understand it. So then I play around with it and see what it does, and see, compare with the other theories, and see, simpler calculations, and see if it gives good results. That was a test, but sometimes it wouldn't give me the test, the expected results that I was looking for. So that's one challenge that I really encountered, and gave me sleepless nights. I think another challenge is writing. Writing is one big challenge in PhD. But I sorted this out by writing in chunks. So everything I was doing, every single bit I was doing, I was working. I wrote something. Whether it was very clear, I still just wrote it. So I had some references to go to, add references. I had a bit of what I thought about it at that time. So when later, when I was then supposed to compile my full report, just edit. But writing is one big challenge. Another thing was deadlines. There were deadlines that I had to meet. Sometimes the pressure of meeting deadlines I also encountered, but then forced me to work sometimes overtime, which is not very good, because then you have to hurry up and sometimes not do a very good job. But that's another challenge that I had. And another time that I also had a big challenge is after the first instance. When I was coming in, there was already data for the first part of my work, which I showed, which is on the paper. But then after that, then I had to look for what to include in my second chapter and the third chapter. So because I didn't have data for the second time, I wrote in a proposal. Some of them were rejected, but one was accepted. So that is a bit of uncertainty at that stage, because you then don't know what next. Either one of the objects within your sample and study it in details, or get another interesting thing, because then whatever develops after the initial stage of your research comes what you have studied in the previous one. So one of them was variability, other interesting process, which I didn't then follow up. So what I'm saying is, the challenge that I encountered is uncertainty of what we are going to do next. I think.
Yeah, no, that's a really good answer.
Thank you.
And thanks for the question, Evans. I'm sure that's of interest to everyone on the call. And I think, I think Willis's journey was fairly, fairly typical of a PhD student. Maybe I can ask a sort of cheeky supplementary one, which is, how well did you feel that the DARA basic training helped, help the transition into the PhD?
Yeah, I think DARA model is one of the best for PhD or master's students. Let me just go a little bit. So before coming to DARA, I had gone to South Africa to study masters. And when I went to South Africa, I went from a pure physics background to astronomy background. And just as a matter of advice to future students is, you don't have to know everything in astronomy to pass your MSc. So I went back as much as reading what happened during Copernicus' time, the history of astronomy, and took a lot of my time trying to understand all that and not concentrating on my project, which was the main focus at that time. And so when I came for my PhD, I had been trained on a bit of radio astronomy, CASA. I knew about how telescopes work. So I just had to build on what was already a foundation that was already placed. So I think their DARA program is, I think, one of the best in that, because then they train you for 8 months, which I would say a postgraduate training. So that when you go in there, at least you know about programming Python, at least you know about CASA, at least you know about other softwares, at least you know about TopCat. We were taught all that. at least you know about how telescopes work, how interferometry takes place, how interference takes place, how signals come in, how visibilities are formed, a bit of some information. So I think it was a very significant part. So what I would say is that doing the PhD, I would call it as 3.5 years, but it's 3.5 plus 2 months that I got as a data basic trainee in Kenya and South Africa. Yeah. Because I also remember when I was in South Africa, I would go to class, I did a coursework, I would be given a task and like take part of the sky and identify the sources and plot this graph and use this code and run this. And I didn't know anything about coding. So sometimes I would just go back home and just wonder why I went for the program. But when I came to Leeds, I had a little bit of ground on a bit of programming, a bit of use of LaTeX, how to write reports. And also another very significant part of the basic training is report writing, because most of the postgraduate work is writing reports. Yeah.
Thanks very much, Willice. And obviously, thank you for that answer. It was not a planted question. And, you know, I think, you know, it's good that, you know, if you are going to do an observational master's or PhD, then, you know, if you've learned the CASA software package already, then that really, you know, leads you nicely into the PhD, and you can start to hit the ground running. Okay, I see Solomon's come back with another question, but I'll, in the interest of spreading the questions around, there's one from Brian. I can't see the full name. Okay, so Brian's asking me to ask it for him anyway. So Brian's question is, coming back to this processing jet again, which obviously is a really very nice picture, obviously left a big impression on the audience. Does the precession affect the acceleration of the jet further from the core?
Yeah, there are still debatable areas of jets, really. One of them is, we know how the jet lobes are accelerated. There is a mechanism called first order Fermi acceleration mechanism. And that is how to accelerate the particles to relativistic levels. But how the particles, which are not lobes, are accelerated themselves, possibly magnetically, but it's still not very clear. Possibly precession can, because there is churning out of material and mechanical energy, but I don't think it's the kind of acceleration that will be to relativistic levels. I think so. Yeah,
I think I would agree. I think an honest answer, maybe we don't know, because it's, you know, it's quite difficult. Yeah. Okay. Well, yeah. Thanks, Brian, and thanks very much for your question. So one final one from Solomon was again, I'll ask it for you, Solomon, just because of the audio problems. So he's asking about, I think again in the paper you mentioned that there might be big uncertainties, maybe systematic uncertainties with the Q-band emission, so the high frequency emission at 43 gigahertz. But obviously, you know, you still used those fluxes to generate your spectral index and draw your conclusions. Can you elaborate a bit on why there might be, you know, big uncertainties on the Q-band and the spectral indices?
Yeah, so Q-band has and of course for VLA, Q-band has one issue. It has a bit of dust in it. So we expect this dust to increase the flux, to raise the flux above the what free flux would be. But in VLA, there is also, because of the lobes, because if you looked at the lobes at L band and C band, you will see that they are extended. And if you look at them, if I had images at Q band, they're point sources. So it could be taking away some of the fluxes, what we call resolving out. So because there's resolving out at Q band and there's dust at Q band, it's difficult to tell what percentage of that flux is free. But because there is that resolving out, part of flux is going, part of flux is coming from dust, we just accepted them. So that's why we say that there's large uncertainties that could be there. But because we also saw that when we did the plots, there was no very weird behavior that would suggest that the dust or the resolving out of flux would affect the spectral index, we just accepted them. But then if you did study if you could read maybe further into the paper, you'll find out that the way that L band and C band was imaged was a bit different. And that was because we restricted what is called UV range so that we could pick emission from similar region for L and C. So L and C was a good check for Q. And because there was no weird behavior at Q, and L and C agreed, because what we thought is they are from the same structures and same size of structures, then we believed in Q. But then, as you said, there is possibility of uncertainty in it. We can't quite tell what it is. We just don't know. We know part of it is free. We know part of it is dust, and we know part of it is lost, part of the flux. That much we know, but we don't know what the percentage that is purely free emission, which would contribute to thermal emission.
Yeah, no, that's very good. You know, we've also been other work that's going on at Leeds where we're even at higher frequency, where we're using the ALMA telescope to observe some of these sources at really, really high resolution, so real cutting edge stuff, the sort of stuff that Catherine Johnson's doing. Then you can actually still see a little point-like contribution to free in the middle of the big dust disk at even at ALMA frequencies, so you know, several hundred gigahertz. So the free continues on upwards. It looks like in these objects. So there's a lot of interest in that crossover point around 50 gigahertz or something like that. Maybe just to finish up, thank you for all the questions from the audience. That's really good. Maybe just one final sort of comment to again raise our eyes and help us look forward. Really, is, you know, you talked about you know, going to South Africa now on the postdoc and the next stage, which is really fantastic. You know, what are you looking forward to with the you know, what's the big new step forward really with the Meerkat sort of L-band survey data that you know, what have we got to look forward to there? And of course, you know, this is a brand new radio telescope on African soil, and you know, we're hoping that all of the African nations will be able to join in with those Meerkat results in the future. So you know, what are you particularly looking forward to there?
Yeah, so one, of course, to ground myself on research and maybe get towards independence in research. That's one. But again, as it is now, South Africa gives data largely to researchers working in South Africa. So because I'll be in South Africa for some time, 3 years most likely, then it means that I will have access to this data. And if we have some of our students back home in our avian countries, we could use part of this data for their research. So that is one. So developing network is one thing that I'll highly focus on. And if I have time, possibly co-supervise some MSCs and undergraduate astrophysics students back home or in any avian countries, anyone who is interested. Apart from that, as I go to South Africa, and of course I have the DARA family, we collaborate more and extend the network so that it's DARA, South Africa, and AVN. And for JET specifically, because there is so now basically on research, because now this is a survey that is done on the galactic plane, and that will be done also at C-band and of L-band data. I am going to identify some of these sources, study them, and because Meerkat or telescope is a slightly larger beam or resolution, so I can then identify the extended emission in these jets. Yeah.
But also, it's, you know, already probably more sensitive than the VLA even. You know, this is, Meerkat is already becoming the world's best radio telescope effectively. So, you know, the sensitivity is incredible. And so, you know, this should allow some new discoveries, and hopefully we can, as you just said, very generously, you know, share that data amongst as many of the African researchers in the AVN partner countries that that we can get involved as we move the whole DARA project forward as well. So I think that's a really good place to end. One thing I've noticed on the new system is that it doesn't seem to have the reaction clappy hand thing that we used to have, but I'm sure you can imagine the audience clapping you greatly. You know, many thanks, Willice, for an excellent presentation and you know, giving us that insight into what the first DARA PhD actually looked like, and a bit about your academic journey as well. So I think I'm just going to hand back to Trish for a few closing remarks as well. I'd just like to thank all the audience again for joining with us. Thank you for sending in those excellent questions. That was a really good range of questions. So many thanks to the audience. Again, keep your suggestions for future topics for this seminar series coming in. Trish will update you on upcoming seminars in a moment, but you know, send suggestions in to me and Trish, and you know, was that a good level for people, you know, because we've got plenty more PhD and master students who could give these kind of talks as well. So, you know, if you like this, then please let us know. Or, you know, any feedback you've got, then that would be good. Okay, Trish, if you can reclaim the host, I think. Willice, you might have to give her permission. I'm not sure.
How do I do that?
I don't think I can do it. You can make someone else the host as well. If you go to the participant list rather than the attendee list and click on Trish's name, I think you can do a make host. Or Trish can push the reclaim host button, I think.
Okay, I can make a host.
Excellent, thank you very much, and thank you, Willice. That was great and encouraging. So thank you everybody for attending. I'd just like to make a few announcements, and also just confirm that we will be sending out a follow-up questionnaire to everybody, and it's important that we do get your feedback, because feedback is valuable and it will help us further improve the e-seminar series. So I will send that out to you within the next couple of days. Just to announce that we have another e-seminar scheduled for the 28th of May, and that is with Professor Ben Stappers from the University of Manchester. And I will just share my screen to show you that. Hopefully everybody can see that. So I will be opening registration again in the next day or two, and I will be sending everybody an email just to remind them that registration is open. So hopefully you can join us for that. And I understand that Melvin's in conversation with one of our colleagues, Steve Jones, to arrange a business development e-seminar. Melvin, would you like to add to that?
Yeah, so probably the following one will be by Steve Jones, as Trish said, who's the DARA business consultant, former commercial director at Goonhilly. Some of you may have met him at the annual network events. He's also been to Zambia on a tour around to meet you know, former DARA trainees there who with business ideas. So quite a lot of you on the first talk mentioned that, you know, you were very keen on hearing a bit more about the sort of business advice available. So he will give a talk on the sort of general principles of building up your sort of business plans and that kind of thing, if you've got an idea for starting out in business. So that will be one talk. Perhaps I'll just mention another one that I'm lining up as well. So Rod Hine, who's also another part-time consultant. He's our DARA antenna consultant at the moment. So, you know, had years of experience working on antenna control systems and worked on the original longer knot dish in Kenya back in the 70s, now retired. But he's going to give one of these as well. He's also interested in, well, he runs an amateur radio club here in Leeds. And interestingly, I just got an email from the African Astronomy Society that is interested in setting up a subcommittee that would help develop sort of amateur radio telescopes, and probably amateur radio, transmissions and communications as well, across Africa. And so Rod would be is very interested in helping setting that up. So I think a talk around sort of this idea of what you can do with sort of amateur radio kit, I think will be forthcoming as well.
Okay, thank you, Melvin. Right, okay, and finally, just to announce that we now have a YouTube channel, so we really are getting techie. The reason we've basically launched a YouTube channel is so we can share these recordings. So the first e-seminar is now available to view, and the second seminar will be soon posted on there too. So please find us on YouTube and subscribe to us so you'll get notifications when we add new content to that channel. But otherwise, that is everything I've got to say. Anything else, Melvin or Willis?
Not from me, I think. Just thank all the audience for turning up and sending their questions in, and hope to see you again for Ben's talk, which I'm sure will be on Pulsars, I guess. He's very entertaining speaker and very informative, so we look forward to that one.
Super. Well, thank you very much, and that's the end of today's e-seminar, and we'll hope to see you soon. Thank you.